Alright, what's up everyone? Welcome back to Structure Free Learning. And in this video, we're going to do our first or introductory example on thermal stress in axially loaded members. And what we're going to do is calculate the effects. In this case, calculate the reactions of a fixed rod that's made of aluminum. Knowing that it's aluminum is important in this case to know that the modulus of elasticity is about 70 gigapascals and the coefficient of thermal expansion, alpha, is 23 times 10 to the minus 6 strain per degree C, or millimeter per degree C, or as it's often written as 1 over degree C. And this rod, a circular rod with a diameter of 50 millimeters, is subject to a uniform temperature increase of 20 degrees C, in addition to an externally applied load of 20 kilonewtons at point C. Segment AC is 400 millimeters long, and segment BC or CB is 800 millimeters long. And what we want to do is find the reactions at the support. And the way that we're going to do this is first to look at or draw a free body diagram and look at the equilibrium equations and find out that this thing is statically indeterminate. With a temperature change and a statically indeterminate component, we're going to experience thermal stresses. Analyze the statically indeterminate component using the force method, and this involves identifying a redundant, removing that redundant, drawing a primary and redundant structure, and then coming up with a compatibility relationship. And hopefully after we've done all that, we'll have one equation, one unknown left, and we'll be able to find one of the reactions and then use the equilibrium equations to find the other. So I'm just going to write solve. Alright, so to get to it, let's just do the FBD. I'm just going to take the drawing that I have here. And because I have an axially loaded member and we're only looking at axial expansion, the only reactions of importance are the horizontal reactions at A and B. And so now if I write my equilibrium equation, and the only one that's available to me in this case is that the sum of the forces in the horizontal equal to 0, and I would have AX plus BX minus 20 kilonewtons equals 0. And what I will find is that I have two unknowns and only one equation, so I am statically indeterminate to the first degree. That means I need one compatibility relationship to solve or figure this problem out, or at least find the reaction. So let's see here. Not only do I have this force of 20 kilonewtons, I also have a temperature increase applied uniformly to this entire structure of 20 degrees Celsius. So let's go ahead and apply the force method. Now the force method, or method of superposition, uses the principle of superposition to help us come up with a compatibility relationship. And it's all about removing a redundant and looking at the deformation due to the loading and adding back that redundant and looking at the deformation due to that redundant alone and coming up with a compatibility relationship. So in this case here, I have two unknowns, one equation. I'm statically indeterminate to the first degree. That means I have to remove one of the redundant reactions. And in this case, I could remove the reaction at B so that my structure will look like this. And now I'm going to apply the loading back to it. By principle of superposition, I can also separate the loading. So I can apply one drawing with the 20 kilonewton load applied to it. I have the same structure with only the temperature change applied to it. These are my primary loading drawings, essentially statically determinate with the redundant removed and the loads applied to it. And then now I have my redundant loading, which is adding back that reaction at B. And I apply that loading back at B the way I initially drew it in my big free body diagram. Now looking at my overall structure, I know that each of these loads causes a deformation at point B. Right here, this end right here represents B, and this 20 kilonewton load will cause some deformation at B. I know that it should contract, but I'm going to assume that it causes some sort of expansion. So here I'm just going to say I don't know what direction this displacement at B is, but I know that this end will move delta at B due to the applied force. Based on my calculations, when I do my cuts, I'm going to find that this should be negative, and that's going to correct it later. And then here with this temperature change, I also get a deformation here. I'm going to again assume an elongation. And I'll say the deformation at B due to the temperature. And then I have the deformation at B here due to my redundant. Now, what I realize from this is that if I look at my overall structure, that point B should not move. The deformation at B in the real structure should be 0. So that tells me that here, based on my force method, I can come up with my compatibility equation, which is that the deformation at B should be 0 in the actual structure. So by superposition, if I add up all three of these components, this thing should add up to 0. The deformation of B due to the applied load, plus the deformation at B due to temperature change, plus the deformation at B due to my redundant, which I'll call Bx. With this compatibility relationship, I've been able to interpret my statically indeterminate problem as three simple axial deformation calculations, one with an externally applied axial force, one with a temperature change, and another with an externally applied axial force, which I'm calling Bx. And so all I've got to do now to solve this is just calculate the deformation at B for each of these three structures and then add them all up together. So for the first case here, with this concentrated 20 kilonewton load applied axially, since I don't have a distributed loading, my segment AC will have a constant normal force, and as well will my segment CB. And my relationship for delta, or the deformation at B due to that externally applied axial load, is just going to be the deformation of C with respect to A plus the deformation of B with respect to C. And if I look at this even closer, this is simply the internal normal force in segment NCA, the length of CA divided by EA of CA, plus NBC LBC over EABC. And what I do know is if I make a cut right here, boom, and I look at the right side of my free body diagram, I'm going to find that this internal normal force is 0. Hey! And then if I make a cut here, and I look at the right side of my free body diagram, which I will do very quickly right here, I will find that here this NAC from equilibrium, NCA, is equal to negative 20 kilonewtons. So essentially that tells me segment CA is in compression. And I'm going to substitute in here negative 20 kilonewtons. And I know the length is 400 millimeters. E and A are given to me, or at least A, the cross-sectional area, I can simply calculate. And so now I can just move on to calculating the deformation at B due to the temperature change. And here, in this case, the deformation at B due to the temperature change is just my linear deformation equation, this alpha delta T times L. And I know alpha is 23 times 10 to the minus 6 per degree C. Delta T is this plus 20 degrees C. And the length of my segment that has this applied temperature change is 1200 millimeters. So that's everything is known here. So yay, I don't even have to mess around with that. And the last part right here, with this 1200 millimeter segment, I have an externally applied force Bx, and that means inside this right here, inside I'm going to have a constant. This constant, which, you know, really this is segment A, B, I'll just call this NAB. I'm going to find that NAB by equilibrium, here is my externally applied force Bx, NAB, and I'm going to find NAB is equal to Bx by equilibrium. And the deformation of B due to Bx is just NAB LAB over EAAB, which really this NAB then is just BX, so BX LAB. Alright, so now I have all the different components of the deformations at B due to the different loads or the redundant, and now I just put them back together by my compatibility equation up here. So by plugging and chugging into my compatibility, one equation, one unknown, and if I multiply through by EA, then I would have, and if I divide by the length, and then I can just go ahead and solve for BX. This Bx is negative 56.55 kilonewtons, which means it's 56.55 kilonewtons pointing in the opposite way that I initially drew it. And so that means 56.55 to the left. And if I substitute this into the equilibrium equation, I will get AX is 76.55 kilonewtons to the right. Well, hopefully that was an interesting and not too complicated example of using the method of superposition to analyze a statically indeterminate axially loaded structure with a temperature effect. Oh man, that was so much to say. Let me know if you have any questions. Practice, just do it. Don't cry, you know the story. Structure free.